In this video lesson, we are going to learn how to take measurements appropriately so that we can convey the quality of our measurement tool. So we're going to start out by talking about our measurement tools, and we're going to talk about what's called precision. Your measurement is limited by the precision of the measurement tool. So what do we mean by that? First of all, precision is basically the smallest decimal place that we can read to. So let's take a look and see what this might mean. So here we have a centimeter ruler, and the smallest increment here is 1 centimeter. That means you are going to have to estimate to the nearest tenths place, right? So you're going to be reading this to the nearest 0.1 centimeter. That means this line, if you are measuring this line, we have to estimate what decimal place that line falls on. And if we look carefully, we might say that that works out to about 6.2 centimeters. Now, could you also say 6.3? Absolutely. This last digit is estimated, and there is a small amount of wiggle room with that, the way you report that measurement. So, of course, within reason. If you said 6.9, that would not make sense. So this last digit that you're always going to be recording your measurement to will always be an estimated digit. Let's take a look, however, when our smallest increment is not 1 centimeter, but our smallest increment is 1/10 of a centimeter. That means you're going to read one more decimal place beyond that. So now we're going to be reading to the nearest hundredths place. So your measurement should be to the nearest 0.01 centimeters. So here, if we're looking at this measurement, 0.4 up to 0.5, maybe this is about 8/10 of the way over. So we would say that this is 0.48 centimeters. This last digit, eighths, that 8 in the hundredths place, is an estimated digit. In this ruler, we see that our smallest increment goes by 10 centimeters. That means our estimated decimal place needs to be to the nearest ones place, the nearest 1 centimeter. So we might estimate here that this is coming down at about 64 centimeters. So you can see here, the decimal place that you report to is indicating not only your measurement, but it's showing you how much information you could read from your measurement tool. So this is what we call the precision of a measurement tool. Precision of a measurement tool is a decimal place, and specifically it is 1 decimal place beyond the smallest division on a measurement tool. So it's 1 decimal place beyond the smallest division. Your measurement, you need to record your measurement 1 decimal place beyond the smallest increment that's on your measurement tool. That means that every measurement has a certain amount of uncertainty. The last digit in the measurement is estimated and is an indicator of the precision of the measurement tool. When you are reporting measurements, you are expected to estimate 1 more digit beyond the smallest increment visible on the measurement tool. That means that there is some uncertainty in every measurement, and that's okay. But if we're all working on the same place, that the last number you wrote down was an estimation, then we know exactly what the precision of your measurement tool was. So let's take a look at a couple of practice problems here. Another couple of rulers here where we're practicing measuring lengths. We have a ruler here that is measured in centimeters. The smallest interval here, if this is 1 centimeter from 7 to 8, then each one of these divisions is 1/10 of a centimeter, right? The smallest interval is the 10th. That means your precision, you are going to read to the nearest hundredths. So I skipped a step here in the your notes. You're not writing down what your smallest interval is. You're writing down 1 digit beyond your smallest interval. That means your measurement needs to be recorded to 2 decimal places. So this measurement is at least 7.5, 7.6, 7, it's not beyond 7.7, so it's at least 7.6. And I'm going to estimate 1 beyond. I don't think it's quite to 7.7, so I'm going to say 7.69 centimeters. Now this ruler is reading in millimeters, so that's the unit we're going to report here. If we take a look here, if this is 87 and this is 88, then each one of these increments represents a tenth of a millimeter. So we are going to read to the nearest hundredths of a millimeter. Right, this is the smallest increment is a tenth of a millimeter, so we are going to read to the nearest hundredths of a millimeter. And it's really, really difficult to do when the intervals are really this small. It's hard to resolve them with our eyesight. But what we see here is this is 87.1, 87.2, 0.3. I'm going to say it falls dead on the 87.4. So can we leave it at 87.4? No, we have to report our precision to the nearest hundredths. Well, if it falls exactly on 4, we're going to say it falls on the 40. Okay, it's 0.40, and the unit here is millimeters. So that's okay to put a 0 at the end. That's actually conveying that you're able to estimate to the nearest hundredths place. It just happens to fall exactly on the 0. Let's take a look at volume in graduated cylinders. Notice here that the volume increments go up from 1, 2, 3, 4, 5. The numbers go up as you go up. What we need to do, again, inspect the scale to see what your smallest interval is. If this from 2 to 3 is 1 milliliter, then these increments are each a tenth of a milliliter. So that means our precision is going to be to the nearest hundredths of a milliliter. That's how far we have to report our measurement to. You always want to read the bottom of the meniscus when you're reading volume. And so the bottom of the meniscus looks like it's reading, let's see right here. If we're reading this part right here, this is 3.1, 3.2, 3.3. I'm going to say it falls exactly on the 3.3, but we need to read to the nearest hundredth, so I'm going to say 3.30 milliliters. The precision on the second example, let's see, from here to here is 10 milliliters. That means each one of these divisions is 1 milliliter. So that means we are going to be reading to the nearest tenth of a milliliter. So let's see, the bottom of the meniscus looks like it's falling just below the 45 mark. So I'm going to say 44.9 milliliters. Last one. This is tricky. This is the trickiest type to read, because if we look here from 6 up to 8, this is a total of 2 milliliters. That means that if this is from this point right here, this is 7 milliliters, and that means that each one of these intervals is 0.2. 0.2 milliliter intervals. So when we don't have intervals that fall exactly on a power of 10, then that is going to limit us. We cannot read this particular instrument to the nearest hundredths because our smallest interval is not a power of 10. So what we're going to say here is that our precision is to the nearest tenths place in milliliters. And if I read the bottom of the meniscus here, I'm going to say it was 6.2, 6.4, 6.6. I'm going to say that this is, looks like 6.8. Okay. Now remember, these last digits are always estimated, so if you had said that that was 6.7, that would be an acceptable measurement. For this measurement, if you had said 55.0, also would have been an acceptable measurement. Going back to this one, if you said 3.29 or 3.31, those also could be considered acceptable measurements. That last digit, as we've said, is always estimated, and there is some uncertainty, some wiggle room there. Now there's another type of instrument that is called a burette. It does measure volume. The difference here is that instead of pouring the liquid out, the liquid is drained from the bottom. And so when we have this type of instrument that drains out the bottom, then the numbers increase, right? So 5 to 6 to 7 to 8 to 9. So the numbers increase as you go down, which is very different than graduated cylinders where the numbers go up. So pay attention to that. This is 5 and this is 6. So we know our measurement is going to have to be between 5 and 6. The smallest interval here is a tenth of a milliliter, right? These are all in milliliters. So the smallest increment being a tenth of a milliliter, our precision is to the nearest hundredth of a milliliter. So let's go ahead and read the bottom of the meniscus once again. So this is 6.1, 6.2, 6.3. The meniscus is above 6.3, but below 6.4. I'm going to say that that falls around 6.34. Okay, that last digit could be anywhere from, I would say, a 4 or a 5, right? There's some wiggle room there. There's some leniency. But the 6.3 is for sure. It's but definitely greater than the 6.3, and it's less than 6.4. So it's only that last digit that there's uncertainty with because it's estimated. Here's another burette example here. Again, the smallest increment is a tenth, so our precision is to the nearest hundredths. So this is, let's see, 38.5. No, 36, that's a 36. 36, 37, so 36.5, 36.6. And I would say this falls exactly on the 36.7. But we have to read it to the nearest hundredths place. And since it falls exactly on the 7, we're going to mark that with a 0. So there's our second burette volume measurement. Now let's take a look at recording mass. These are digital scales. It's kind of hard to see on this small picture, but this is a scale that can read to the 0.00 grams. So with a digital scale, the last number that they report to you, that is the estimated digit. You do not have to do any estimating for a digital scale. They are telling you that the precision here is to the nearest 0.01 gram. It's telling you that you should read these measurements to the nearest hundredth, to 2 decimal places. Okay, so there's nothing on this measurement, but you would report this as 0.00 grams. That's how it is meant to be reported, to 2 decimal places. Now this digital scale, it's hard to read again, but this is 0.54, let's see, is that a 7? I think that's a 7, 0.547, okay, grams. They are telling you that this right here, this last digit, is the estimated digit, and that is the precision with which you should record any measurement from this particular scale. So this scale can read to the nearest thousandths place, 3 decimal places. So this measurement, you would record this as 0.547 grams. That's the nice thing about digital scales. Whatever numbers appear on the screen, that is the measurement that you record. Now you might be asking, do I have to write down the 0 in front of the decimal? It's good practice too. If you don't include the 0 in front of the decimal, sometimes that decimal is not as obvious. Putting the 0 in front of it kind of highlights, it kind of flags that there's a decimal right there. All right, so all of the examples we've done so far have been you as the scientist recording the measurement. You're the one in these examples, you've looked at the instrument, you've recorded the measurement. But that's not always going to be the case, right? There's going to be times when you are going to have to look at someone else's measurement, and you are going to have to determine the precision of that instrument. So when a measurement is made by someone else, you can look at that measurement and determine the precision of the tool that they use to make the measurement. It's important to remember that the last digit of a valid measurement is always estimated. The decimal place of this estimated digit is how we describe the precision of a measurement. Remember, the precision, when we ask you for precision, we are asking you to report a particular decimal place. Now this can get a little tricky whenever zeros are at the end of numbers, especially those values that are larger than 1. So we have some weird rules that are going to convey the precision of the measurement tool and therefore the precision of the measurement. So let's dive into these rules. To do that, first you're going to look at the number and determine if a decimal point is visible, meaning printed. Do you actually see the decimal point printed on the paper or on the screen? If the decimal point is visible, meaning it's actually printed, then the precision is the decimal place of the rightmost number, the digit that's all, the decimal place all the way to the right of the number that's reported. If the decimal point is not visible, the precision is the decimal place of the rightmost integer, integer being a non-zero number, or a 0 with a bar over it. And what that's going to look like is this. It's going to be a 0 with a bar over it. Okay, so we are going to take a look at some of these examples and figure out what that's going to look like. So we have a measurement. It's less than 1, 0.30 grams, right? And what we are going to say here is that the precision, the decimal point is visible. So when we see that it's visible, we look at the rightmost decimal place. And that right there is the nearest 0.01 grams, the nearest hundredths place. Let's see, for these numbers that are larger than 1, right, we see a decimal point visible. So we are just looking at this last decimal place, right? So the precision here is to the nearest thousandths place, right? This is the thousandths place. Now look at this. We have a decimal point that is visible. This is not typical. You would never see this in a math class. But this decimal place here is purposeful. Even though there's no numbers after it, this decimal point is put here so that you know that it's visible, so that we can look at this last 0 and know that the nearest ones place, so the nearest 1 milliliter, the ones place is the precision. And I just realized that this shouldn't have been grams, this should have been centimeters. Okay. All right, now these last two are numbers that are larger than 1, and there is no decimal point visible. So without a decimal point being visible, we then go and we say that the rightmost non-zero number, that decimal place, which is the nearest 100 kilometers, the nearest hundreds place, not hundreds, hundreds place, the nearest hundreds place, that is the precision of that measurement. They had to estimate to the nearest 100. Now, what if you have a situation here where you want to say that you want to estimate this number to the nearest tens place, and it's a 0? Well, in that case, we put a bar over the 0. We can't put a decimal place there because that would change the magnitude of the number. So what we are saying here is that the nearest 10 kilometers, the tens place, is the precision of that particular measurement. So we have a few tricks here where we can convey the precision of a measurement if the decimal place is not visible, or if you wanted to say that the ones place and it's a 0, that is the precision of that measurement. So what does this all mean? What does this all mean? Well, this is a concept known as significant figures. Significant figures is the number of digits in a measurement that are used to express the measurement to the appropriate precision. Remember, precision is just a decimal place. based on the limit of precision of the measurement tool. So this is all about trying to convey information about the quality and the precision of your measurement tool, right? So we say that by using significant figures, we can show the precision of a measurement. Now, significant figures sometimes gets to be a mouthful, so we sometimes will abbreviate it as sig figs. Okay, it's the number of sig figs. The number of significant figures in a measurement equals the total number of digits from and including the first leftmost integer, non-zero digit, in the measurement all the way to the limit of precision of that measurement. Whoa, what is that? That is a very cumbersome definition that really this definition is best learned by doing lots of examples. So one way that you can figure out how to do this, you won't have to do this all the time, but this is one way to kind of get you in the habit of being able to look at a measurement and knowing how many significant figures are in a measurement, right? What we want to do is significant figures needs to include all the way to the decimal place that represents the precision of your measurement tool. So let's start with this first example. We're going to start by circling the first leftmost integer, integer being a non-zero number. So that's our first leftmost integer. Now, circle the digit that shows the limit of precision. This is where we look. Is there a decimal point visible? Yes, there is. So the rightmost integer is the limit of your precision. Now, count the total number of significant figures, which includes the circled numbers and all the numbers in between. So this measurement has 1, 2, 3, 4, 5 significant figures. Our second measurement. First, circle the leftmost integer. That's the 8. Now, circle the digit that shows the limit of precision. No decimal point visible. No decimal point visible. So that means that the limit of precision is also the 8. Okay. So this is one significant figure. That means this person had to round to the nearest thousandths place. The third measurement, we're going to circle the first leftmost integer, that's the 4, circling the digit that shows the limit of precision. A decimal point is visible, so it's the rightmost number. Okay, so this measurement has 2 significant figures. In our fourth measurement, the first leftmost integer is the 2. The digit showing the limit of precision, to do that, we look for the decimal. It's visible, so the rightmost number. This has 4 significant figures. In our next example, our first leftmost integer is the 2. To find the limit of precision, there is no decimal point printed, so that means I can only circle the rightmost integer. So this measurement has 2 significant figures. Our third measurement, I'm going to circle the 2. That's our first leftmost integer. Now, our limit of precision, the bar is showing that this is my limit of precision, so I'm going to circle that. This has 3 significant figures. All right, these next values, these are all less than 1. You know, these are all measurements that represent less than the quantity of 1. So we have a 0 point. They all start with 0 point. So circling the first leftmost integer, we do not include the leftmost 0. So I'm going to start here with a 7. And as for the limit of precision, there is a decimal point present. So that means I circle my rightmost number. This measurement has 3 significant figures. In my second to last example here, my leftmost integer is the 9. We do not count zeros that begin a number as significant because they are placeholders. You could put this number into scientific notation and those zeros would disappear. So our first leftmost integer is the 9, and our limit of precision is the 3, because a decimal is visible, so we circle the rightmost number. This measurement has 4 significant figures. In our last example, our leftmost integer is the 5. The limit of precision, with a decimal present, we circle the rightmost number. This measurement has 5 significant figures. So we're going to get some more practice with this, but remember, the last of the sig figs is the estimated digit. So the 5th number here, the 5th significant figure, is always the estimated digit, right? So every one of these last numbers that I've circled represents the estimated digit. You weren't certain about it. Someone had to interpret what that value was between the smallest interval. All right, this was a very big lesson. This is a skill that you're going to be using quite a lot for the rest of the year. So hopefully you were able to follow along with this. What we talked about here was the precision of a measurement tool. We learned how to appropriately write the measurement so that the last digit that you wrote down represented an estimated value. We did that because the estimated digit is included as part of what we call significant figures. Significant figures is a way to look at someone else's measurement and be able to determine what that measurement tool's limit of precision was. All right, that's it for this video lesson. We'll see you back in the classroom.